Welcome back, ladies and gentlemen. Here we go, talking about friction. So, you know that if I set a block on this surface here, that gravity will be pushing it down and the table is pushing it up, providing those two forces. And we can quickly diagram what's going on with this block and see that, well, okay, it has weight pulling the block down and the tabletop surface is providing a support force upward. We would call that a normal force. That's easy enough to understand. And the block right now is in equilibrium. Now, if I push on it and it doesn't go anywhere, then, yeah, I'm trying not to get it to move to show you without moving. There's something happening here. I'm going in there and I'm pushing on it, applying a force to it. Now, granted, it's a very small force, but that doesn't really matter right now. Force applied, right? But we notice that it doesn't move. There's no acceleration anywhere, so this force has to be balanced. And it turns out that as soon as I create that applied force, then this other brand new force shows up, and it is friction. And it is the friction between these two surfaces. They're not moving, but they would tend to move. So there's a new force, the force of friction. Now, with no movement, we call that static friction. And static just meaning not moving. That actually does matter. Now, there's another situation. I could apply a force to it and I could get the block to accelerate. And that, forces are clearly unbalanced. And when they're unbalanced, I really have no way of saying much about the friction involved. But what I can do instead is push on it and move it at a constant velocity. And a constant velocity means that there's no acceleration, and that means forces are balanced, we have equilibrium, and that's interesting because then we still have weight pulling it down, that hasn't changed, and we still have the normal force pushing up, that hasn't changed, but my applied force, so I was pushing to the left, so let me draw this to the left here, was larger. And now what we see, though, is constant velocity. Here there was no velocity. Here we see constant velocity. And so acceleration is still zero. So there's still friction, and there is this brand new friction force opposing that motion. Motion is that way. Friction always opposes motion. And so it's going to be pushing this way. And I want to draw it the same length as that arrow. There's my friction. But we have motion here, so I'm not going to call that static friction. There it is. Sorry, it's more visible for you now. I'm going to call that kinetic friction because it's moving. Kinetic friction force. And anything kinetic just means there's motion associated with it. Alright, so there's a lot going on with friction, particularly things that matter and things that don't. For example, I've got this block and it creates a certain amount of friction. Now, if I were to push this block across the bare tabletop, it's on a different surface. It's not the paper anymore, it's the tabletop. And because of the qualities of the material, it would be a different amount of friction. One thing I can also do is I can turn the block on its edge. And on its edge, it's got less surface area in contact. And so you think, whoa, that's got to change the amount of friction. But it doesn't. It turns out that doesn't change anything. And there's another thing I could do. I could add some mass. I could make this block heavier. And when I do that, it's actually harder to move. Not harder to move because of the mass, although that is true. But there's more friction between the block and the piece of paper. So there's several things that don't really affect friction, but several that do. So what are the things that do and don't affect friction? Well, okay, let's answer this. First, it seems like the weight affects the friction. This is an important deal, but it turns out that it really isn't weight that matters. It's not the downward force that matters. It's this guy. It's the upward normal force that really matters. Now, in this situation, normal force is equal to the weight. Easy to understand that. It's equilibrium vertically. But we've got to train ourselves to think about normal force. The amount of friction does depend on normal force. No, sorry, not equal sign. I don't want to do an equal sign. So with normal force, larger normal force, larger friction force. I'll just use a lowercase f here for friction force. And that's true with static friction and with kinetic friction both. Edge the paper off. Okay, now what else? So we know normal force does affect the amount of friction. Surface area does not. The amount of surface area in contact does not affect the amount of friction. Speed of the movement. Speed of the motion, how quickly it's moving. That's, we could test that if we had to, and it turns out that does not affect friction either. Certainly doesn't affect static friction because there's no movement, but also it doesn't matter with with kinetic friction how quickly it's going. What else? The type of surface. Well, yes. All you have to do is think about skateboarding, and skateboards on the top surface, they usually put grip tape, which is a lot like sandpaper stuck to the top of the board, and you know that. So why? Because the roughness of the surface increases the grip between the board and the shoes. And so there's, about the types of surface, there's just lots of variety, I'll say. But yes, it absolutely does affect friction. Lots of variety. Now, a couple other things here. Let me clear this out. Check this out. We know that the normal force is very much related to the amount of friction. And if we were to investigate, get some data, and say, you know what, I want to see how much friction there is. Let's go with kinetic at first. How much kinetic friction there is, and compare that to the normal force. What I'm going to see is a very linear relationship. And what's interesting here is the slope of this line actually has some physical meaning for us. But first of all, we know it's a line, so it's going to take the form of y equals mx plus b. That's a linear relationship, a very general kind of thing. But b is 0, so that kind of just goes away in this point. Well, why is the y-intercept 0? Well, when normal force is 0, there is no friction force. So that's a good thing to remember. Now, what are the y values? The y values are kinetic friction force. What are the x values? The x values are normal force. Okay. Now, m is the slope of a line. And what is the slope of our line here? You know how to find slope. You find 2 points on the line, make them as far apart as you can, and you look at the rise and you look at the run. You've got a change in x values, you've got a change in y values. Those are your run and your rise. And do a division problem. So basically, it's rise over run. Cool. And so let me set that up over here, because I got some room over here. So slope. Rise over run. Easy enough. But look at this. The rise is going to be made up of values that are kinetic friction values. The run is going to be made up of values that are normal force values. So this slope is basically kinetic friction divided by normal force. And I keep saying kinetic friction, but that is a force. Friction is a force. I don't want to ever forget that. So this is interesting. The slope of this line is equivalent to force divided by force, and that's newtons divided by newtons. And that looks like it sure cancels out. Now the numbers don't cancel. You do the math, you do the division with the numbers, and you get an actual slope. But this final answer that you get for the slope of this line does not have units to it. And so you calculate some number, and it's just a number, just a ratio of the two forces, really. In physics, we have a name for that ratio, and it's called mu. So it looks like, kind of like this. I think you would say like mu, like that. It's a Greek letter, and it's called, this is what you say when you name this symbol, but what you say if you're talking about it in terms of physics is basically it is the coefficient of friction. Coefficient. Oh my goodness, there we go. Okay, and so we put that symbol into our equation right here. Well, because this is where the slope resides. It's multiplying by the x values right there. Now, specifically, we are looking at kinetic friction right here. So this is going to be the coefficient of kinetic friction. Put a little k right there. So this is an equation that you want to be rather familiar with. And it is just like this equation for a line. But there's the slope of the line. It's the coefficient. And that slope is constant, so that number does not change. Oh my goodness. A constant slope does not change. Now, could we do something similar if we were to look at, let's say, static friction instead of kinetic friction? We're going to have a new line. Now, this is going to be interesting. What you will find is that static friction is typically a little bit larger than kinetic friction. And we got to qualify this in a little bit. I'm going to have a different slope and a steeper slope, because at the same normal force, the static friction will be a little bit higher than the kinetic friction. You see that difference vertically. Okay, well, we're going to have 2 points on that line, right? We're going to have a run, we're going to have a rise, and so we can find a slope of that line. So this is basically still linear, so we still have y equals mx plus b. The y values are still a friction force, but it's now static friction force. And the x values are still normal force. But now, the slope of this line, the thing that goes in front of normal force right here, is still a mu. It's still a coefficient of friction. But it is not kinetic now. It's a static coefficient of friction. Coefficient of static friction. So here's the corresponding equation that you want to be familiar with and ready. Oh, sorry, you couldn't see that. There you go. Ready to use. Okay, but there's something really interesting. The kinetic friction is easy. It is what it is. But the thing about the static friction, you gotta watch this, because I'm gonna wrap up this video with this last idea, and it's basically this. Okay, I'm going to add that mass. I have this block on the paper, and got my spring scale. Spring scale is pretty well calibrated like that, right? So now, I'm going to get the paper sliding this direction underneath the block. So there's a velocity of the paper that way. Okay. And really what this means is we're sort of simulating a velocity of the block that way. Now you won't see the block move and you won't see the scale move, but you'll see the reading on the scale change somehow. It'll go to some value. So we're creating a relative velocity, and that's really what matters. So if the block is tending to move that way across the paper, then friction will be tending to act this way. And if the paper's moving, it'll be kinetic friction. If the paper is not sliding past the wood, it'll be static. So this could be static or kinetic. It's just a friction force. That's all that's going on right there. I'm not getting specific. For example, I can show you static. There's no sliding, no sliding, no sliding, no sliding, no sliding. Oh, it just slid. Or I can show you kinetic, where it kind of moves and continues to slide at a constant velocity. Okay, gotta go back to the static. This is the issue we must deal with. So I'm going to clear this out, and there will be a friction force this way. It will just be static friction. Okay, but remember, before I start pulling on it, that value is 0. The friction is created in response to a tendency to move. So our tendency of the block to move is to the left. Friction will be to the right. And here's the deal. I'm going to pull a little bit, and you see on the scale a little bit of friction created. Because as hard as I'm pulling that way on the block, friction is pulling the other way on the block, that way. I can pull a little harder with the scale, and you can see still no motion. So the force of the scale here is still equal and opposite to the force of friction the other way. And so here's what we're learning. Static friction isn't always the same value. Even if nothing else changed, the static friction could be as low as 0, or a little higher than that, or a little higher than that, up to some maximum value. Oh, it just slid. So I can find that maximum value, watch the scale, and right before it slides, we see a maximum value. When's it going to happen? Oh, it just happened. And you can see that it went back down. So the thing about static friction, this does not happen with kinetic friction, only static friction. We have to modify that equation that we wrote down. Static friction. We're not going to write an equal sign. We're going to say that it is less than or equal to coefficient of static friction times normal force. So could the static friction be larger than what you do over here? No. It could be equal to what you do over here, but it also could be less than that. It could even be down to 0. So it kind of depends on the situation you're talking about. But we want to keep that in mind, that we really should not use an equal sign until we know more about a certain situation that we're going to be analyzing. All right, that's it for now. That's enough for now. Thanks for watching. I'll catch you next time. Oh, time out. That's not it for now. Just kidding. I need to explain something to you. We've got this thing called the coefficient of friction. Coefficient of static friction or coefficient of kinetic friction. All right. Sometimes, I write it almost like a cursive M, a weird M. Once in a while, you'll see the symbol like that as well. I don't write it so formally and all that business. You'll see me write it like this. But here's the deal. Where does this come from? What is this related to? This is related to the type of surface, or the type of the two surfaces in contact. You'll read about this in your textbook. For example, the tabletop might be a little slipperier than the paper, but both of those are not as grippy. They're both a little more slippery than the surface of the wood. If I were to slide something across the surface of the wood compared to the surface of the paper, it's a little easier on the paper. And grip tape on the skateboard is very rough and would give you a different coefficient of static or kinetic friction, much larger value because it's so grippy, it's so rough. Think of a car's tires driving on the roadway, and then the tires hit a patch of ice in the wintertime. And why is there a danger of the car skidding out, losing control? Well, because the combination of the tire and the roadway provides a certain amount of friction force. It's the types of surfaces that matter. But when the tires hit the ice, that's a different combination of surfaces, and it's a different coefficient of friction, and a much lower one. So overall, you get less friction on ice with the tires than you do on the roadway with the tires. That's why ice becomes very dangerous sometimes. So anyway, just wanted to add that. Thank you for watching, and I will catch you next time.